We're going to finish up chapter 4 and section 4.7 on inverse trig functions, and the name kind of gives it away what we're going to talk about. I have up here a rough drawing of what most of you will remember as a 3, 4, 5 right triangle. 3 squared plus 4 squared equals 5 squared. What I want to know is what's the measure of the smallest angle of this 3, 4, 5 triangle, which I'm calling theta. Alright, you probably already realized that they love using Greek letters for the variables for angles. If we have this, we know all 6 trig functions, but the one I'm just going to pick on is I know that the sine of this angle, and I know this is the smallest angle because it's opposite the shortest side, and I know that the sine of this angle would be the opposite over the hypotenuse. It's a 5 there if you can't read it, that's 3/5. So I'm going to write that here, that the sine of theta is equal to 3/5. So I know that the sine of an angle is a number. What I need to do is figure out what angle is it whose sine is 3/5 or 0.6. Now that's not a special value. It's not from the unit circle, so I can't get lucky that way. But instead, what I'm going to have to do is I'm going to have to kind of reverse the process of taking the sine of an angle and getting a number. I want to undo this. I want to take the inverse of this sine function. But not the inverse of the sine function of the angle. We're reversing this. Remember, the angle is my independent variable. This is my dependent variable, in that I plug in an angle, I get a value. This is my x, this is my y. I'm going to reverse this. I need to figure out a way to find the inverse sine of 3/5 and find out what angle corresponds to that. Now, you probably already know, I've drawn a picture here, very rough picture here, or the graph of the sine function. And you can see that this is not a one-to-one function. So you say, well, you can't have an inverse sine unless the sine is 1-to-1. And you're absolutely correct. And here's where, depending on the textbook you use, you'll get different notations. What they do is they kind of define a special version of the sine function. Sometimes they'll just use like a capital S, sine of theta. And what that is, it just restricts the domain. The domain for the parent function sine is all real numbers. We're going to restrict it between negative pi over 2 and positive pi over 2. If you look at the part there just that's graphed in purple, and you try the horizontal line test on this, it will pass it. This is a one-to-one function. And therefore, this version, this restricted domain of the parent function sine, is 1-to-1 and has an inverse function. And we use 2 different notations for this inverse function. Sometimes what they'll do is they'll write the inverse of sine with a little -1 like that. But a lot of people get messed up with the notation thinking this means to the -1 power, like the reciprocal. But this is not the reciprocal exponent of things. If I want that, I'll put parentheses around the expression. But I'm going to write something that looks maybe more like this, where y is equal to the inverse sine of x. This is the notation. A little bit more old school is the notation where they put the word arc in front of the abbreviation of sine here. And it means the same thing. It's based on this guy right here. Now what happens is the domain and the range get switched. Now for this guy right here, my domain is from negative pi over 2 to pi over 2 inclusive. My range is from -1 to 1. For this guy down here, it switches. My domain is from -1 to 1, and my range is from negative pi over 2 to pi over 2 inclusive, or from -90 degrees to 90 degrees inclusive. So what happens here is we take the sine of an angle, we get a number. We take the inverse sine of a number, we get an angle. Now this is not the graph here. This is the graph right here. This guy's got a different graph because you have to interchange the x and the y. And you say, well, if I interchange the x and the y, it's a reflection in the line y equals x. Now, here's the problem. Because I decided to be so efficient about this, I have this tick mark here worth pi over 4, which is a little bit less than 1. Pi over 4 is about 0.77 if I'm not mistaken. So this tick mark is about 0.77. This tick mark here is 1. So if I was to try to draw the line y equals, and I'll never do a good job on this. I can never do this. Besides, notice how thick this is. It would be something like this. And I would reflect this graph in here. Now I'm going to do that for you here best that I can, and I'll use a different color here. Notice here, I've got it formally stated that the inverse sine function, or arc sine, denoted inverse sine or arc sine, is the inverse of the restricted sine. That's what I was talking about here with the capital S. The restricted sine function, y equals sine of x, for my values of x between negative pi over 2 and pi over 2. This would be the first quadrant, where it's positive, and the fourth quadrant, where it's negative. The sine values are negative. And as you can see here, this notation is the same as this, whether you're using the inverse sine or the arc sine. It has the same meaning. And here's where you can see how I switch the domain and the range around there. So what I'm going to do here is I'm going to try to come up with a halfway decent sketch. Well, me coming up with a halfway decent sketch and a real sketch, that's two different things, but we'll give it a shot right here. It's right about here. I'm going to give it a shot. It's not going to look great. And right about here. And best I can. And you can see here now that this guy is the one graphed in green. And so the sine, inverse sine curve looks a little strange. You can see it's reflected in this line, and the line in blue here, again, is the line. I don't have my blue pen, there it is. This is y equals x. Because we know how the graphs of inverse functions are related to one another. One's a reflection of the other in the line y equals x. Now let's jump over to here. Find the exact values or state the expression is undefined. Now what that means is, we're used to taking the sine of an angle and getting a number. We're going to do the inverse sine of a number and see if we can get the angle that corresponds to it. So what I like to do is I like to rewrite this. I like to say, well, this is some... I thought I was going to rewrite it anyway. Maybe my pen stopped. My pen has stopped. Heavens to Murgatroyd. Let me try this one, see if this one's any better. This one's no better. Well, try this one. Here we go. We're going to call this angle, this time, just to break it up, I'm going to call it alpha. And I know that the sine of alpha is the square root of 3 over 2, and I know something else about alpha. Alpha has to be between negative 90 and 90 degrees inclusive, or negative pi over 2 and pi over 2 radians inclusive. So now, square root of 3 over 2, that's a value I remember from my unit circle, and I know that this is going to occur at 60 degrees, or pi over 3 radians. And that's how I find it. So this value here, the inverse sine of square root of 3 over 2, is pi over 3 radians, or 60 degrees, however you want to write it. I'm going to do the same thing right here. I'm going to call this angle beta, just to give it a different name. And that means that the sine of beta is equal to negative 1. That means I have to find an angle, again, between negative 90 and 90, or between negative pi over 2 and pi over 2 inclusive, such that the sine of it is negative 1. Well, the sine of 90 degrees is positive 1. The sine of negative 90 degrees is negative 1. So beta would be negative 90 degrees, or negative pi over 2. And I'll go ahead and write it out there in radians. One more here. Let's call this one, let's go back to theta. Don't want to throw too many Greek letters at you. By the way, you got to remember that Greek alphabet. I talked to you about that before. Alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, omicron, pi, sigma, pi, rho, sigma, tau, upsilon, pi, chi, psi, omega. Okay, now, this is an angle between negative 90 and 90 degrees inclusive, such that the sine of this angle is negative 3. Oh, stop right there. There's no way that we can come up with a value here, because we know sine is never smaller than negative 1. So in this case, we're going to go ahead and state that it's undefined. Now, there are 6 trig functions, and there are 6 inverse trig functions. Now, if you think about the graphs of the 6 parent trig functions, they're all not one-to-one, just like sine over here. However, by restricting the domain we can rewrite this and get a restricted cosine function, a restricted tangent function, a restricted cotangent function, and so on. Now we also know that we have three trig functions that are reciprocals of the other three. Sine and cosecant, cosine and secant, tangent and cotangent. We don't need six trig functions, inverse trig functions. We really only need three. One for sine, one for cosine, and one for tangent. Because if we have those three, we can get the other three, the values for the other three by using some reciprocals and such. I'll show you here as we get through this. Now I'm going to go ahead and just at least show you the graph here for cosine. This is the parent graph for cosine, and you can tell it's not 1 to 1. But again, if I restrict the domain, in this case, not between negative pi over 2 and pi over 2, because it's all positive there, I would go from 0 to pi. There I get all the positive values and all the negative values. And that is 1 to 1. And again, some books will call that capital C cosine of x, where you have the restriction that the domain is from 0 to pi, and the range, of course, is from negative 1 to 1 inclusive, and inclusive up there as well. Let's rewrite this using the same kind of notation. We're going to come up now for the inverse function of cosine. We're going to write y equals inverse cosine of x, or y equals the arc cosine of x. Now, again, the x and the y here are not the same as the x and the y here, because to find the inverse, you have to interchange them. I would have to switch these around. X equals restricted domain cosine here of y, and then solve for y. Well, I have to get rid of the cosine, so I take the inverse cosine of both sides. And the inverse cosine of this cosine that's restricted is going to be just y. And that's how I come up with this notation. I didn't write that out here. I apologize. Probably should have started off showing you that. The x and the y are different. I'm still using the independent, dependent variables, but now I flip-flop those values. So now the numbers I'm plugging in here for x are not angles. They're values between negative 1 and 1 inclusive. And the value y that I get when I take the inverse cosine of these numbers is going to be some angle between 0 and pi inclusive, or between 0 degrees and 90 degrees inclusive. And as you can see here, we've got a little bit of fancier work if I'm going to go ahead and come up with a halfway decent. And I say halfway decent because that's at best what I'm going to be able to come up with. Here's my line. Okay, well, that's supposed to be the line y equals x. Now, if I reflect, and I'll use red this time, if I reflect this graph here, I'm going to get something that's going to look a little bit more like about like this. It's going to go through here, it's going to go through here, it's going to go through pi over 2, which is about 1.57. I'm going to try to get this halfway decent. Ew. So far it's not so good, and then this continues this way, so this will continue this way. And not so good. As my mom likes to say, not so good there. But I think that's going to have to suffice for right now. That's the graph right there in pink for the inverse cosine, just like the one here in blue is the graph for the restricted domain, y equals cosine x. Now what we're going to need to do is we're going to need to do a few values, finding some exact values using inverse cosine or arc cosine, just like we did with sine. But my board's pretty well filled up. We'll just kind of start with that in the next video.